Hey, welcome. Take a moment and settle in. Curiosity brought you here, and if you follow it, it tends to take you further than you expect. Subscribe if you enjoy that journey. Now, let's start at the beginning. You begin by letting your breathing slow, allowing your attention to rest on a simple question that scientists have asked for more than a century. What is spacetime? The word itself sounds complex, but the idea grows from careful observation rather than abstraction. For most of human history, space and time are treated as separate. Space is where things are. Time is when things happen. Clocks tick forward at a steady rate, and distances seem fixed and reliable. This view works well for everyday life, and for a long time it appears to explain the universe accurately. As measurements become more precise, small inconsistencies begin to appear. Light behaves strangely when measured at high speeds. Clocks moving quickly do not keep time in exactly the same way as clocks at rest. These effects are not imagined. They are measured repeatedly using experiments that can be checked and repeated. To explain these results, Albert Einstein proposes that space and time are not separate after all. They are woven together into a single structure called spacetime. In this framework, space is no longer a rigid container, and time is no longer an independent flow. Instead, every event has both a location and a moment, inseparable from one another. When you measure how something moves, you are always measuring its path through spacetime. This idea is confirmed not through philosophy, but through equations that match observation with remarkable accuracy. One of the most important insights is that spacetime is not passive. It does not simply exist while matter moves through it. Mass and energy actively influence the shape of spacetime itself. This influence is what people traditionally call gravity. Rather than imagining gravity as a pulling force acting across empty space, general relativity shows that objects follow the natural paths created by curved spacetime. You can picture this without distortion by thinking of measured trajectories. Planets orbit stars not because they are being pulled by an invisible line, but because the geometry of spacetime around the star guides their motion. The equations describing this behavior predict the exact shapes of orbits, and those predictions match what telescopes record. Mercury's orbit, for example, shifts in a way that cannot be explained by older theories, but fits precisely within Einstein's description. Light, which has no mass, is also affected. When it passes near a massive object, its path bends slightly. This effect, called gravitational lensing, is observed during solar eclipses and through modern telescopes studying distant galaxies. Light from faraway objects is stretched and redirected as it travels through curved spacetime, producing arcs, rings, and multiple images that can be measured and analyzed. These observations are consistent across independent instruments and research teams. Time itself is influenced in the same measurable way. Clocks positioned in stronger gravitational fields tick more slowly than clocks farther away. This is not a metaphor. Atomic clocks placed at different altitudes record different rates of time passage. Satellites orbiting Earth experience weaker gravity than clocks on the ground, causing their onboard clocks to run slightly faster. Engineers must correct for this difference continuously. Without those corrections, GPS navigation would drift by kilometers each day. The system works precisely because spacetime behaves exactly as general relativity predicts. You may notice how calm and reliable these confirmations are. They do not rely on rare events or distant speculation. They operate quietly in technology you use, in signals exchanged between satellites and receivers, in timing adjustments calculated every moment. Spacetime reveals itself not through drama, but through consistency. Another important feature becomes clear as you settle into this understanding. Spacetime is flexible but not fragile. It can curve and stretch under the influence of mass and energy, yet it remains mathematically stable. Even in extreme environments such as near neutron stars or black holes, the equations continue to describe behavior accurately up to known limits. Scientists do not observe spacetime tearing or breaking. They observe it responding smoothly even under enormous stress. To describe this behavior, physicists use geometry. Distances and durations are calculated using spacetime intervals, quantities that remain consistent even when observers move differently. Two observers may disagree about lengths or time intervals, but they agree on the underlying spacetime structure. This agreement is essential. It allows physics to remain objective and testable, regardless of perspective. You may find comfort in how grounded this framework is. Every claim rests on measurement. Every equation is tested against reality. When predictions fail, scientists revise the theory or identify missing information. This process keeps spacetime from becoming an idea based on belief. It remains a model continuously checked by observation. As your thoughts slow, it becomes easier to accept spacetime as something real, not abstract. It shapes the motion of planets, the flow of time in satellites, and the paths of light across the universe. It is not a stage built for events. It is part of the events themselves. Everything that happens unfolds within this shared structure. There are still boundaries to what is known. At extremely small scales, where quantum effects dominate, spacetime behaves in ways not yet fully described. At extremely high energies, current equations reach limits. These are not signs of failure, but markers of where understanding remains incomplete. They invite careful investigation, not speculation. For now, what matters is how much has already been confirmed. Spacetime exists as a measurable framework linking motion, gravity, and time. It responds predictably to mass and energy. It connects the smallest precision experiments with the largest structures in the cosmos. As you rest with this idea, the universe feels less chaotic and more ordered, governed by relationships that reveal themselves slowly, through patience and observation. The more closely spacetime is measured, the more clearly its structure emerges, inviting deeper questions about how geometry itself shapes the universe you quietly inhabit. You settle into the idea that geometry is not only something drawn on paper, but something woven into the universe itself. When scientists speak about the geometry of spacetime, they are not imagining shapes floating in emptiness. They are describing measurable relationships between distance, time, and motion. Geometry becomes a practical tool, grounded in observation, used to describe how objects move and how light travels. In everyday experience, geometry feels simple. Straight lines stay straight. Parallel lines never meet. Angles add up in familiar ways. This kind of geometry works well on small scales like rooms, roads, and buildings. For a long time, scientists assume the universe follows the same rules everywhere. Space appears flat, predictable, and unchanging. Time flows evenly, unaffected by location. Careful measurements begin to challenge this comfortable picture. When astronomers track the motion of planets with increasing precision, they notice subtle deviations. These deviations are small, but persistent. They cannot be explained by assuming space is perfectly flat and time is absolute. Instead of abandoning observation, scientists refine their tools and calculations. General relativity provides a new way to describe these results. Geometry becomes flexible rather than rigid. Spacetime can curve, and that curvature determines how objects move. This idea does not replace measurement with imagination. It replaces old assumptions with equations that match what is observed. In curved spacetime, straight lines are redefined. The shortest path between 2 points is no longer what appears straight to the eye. It is the path that follows the underlying geometry. Objects moving freely follow these paths, called geodesics. Planets orbit stars because they are following geodesics in curved spacetime, not because they are being pulled through empty space. This geometric description is tested repeatedly. The orbit of Mercury provides one of the clearest confirmations. This path shifts slightly over time, an effect that classical physics cannot fully explain. The geometric equations of general relativity predict this shift exactly. No adjustments are needed. Observation and theory align quietly and precisely. Light offers another powerful test. When light passes near a massive object, it follows the curved geometry of spacetime. This path bends by a small, predictable amount. This bending is measured during solar eclipses and through detailed observations of distant galaxies. Multiple images, arcs, and rings appear exactly where geometry predicts they should. These patterns are not artistic interpretations. They are measured distortions, mapped carefully across the sky. You may notice how geometry simplifies understanding. Instead of imagining invisible forces acting at a distance, motion becomes a response to structure. Objects move the way they do because spacetime is shaped the way it is. This perspective removes unnecessary complexity while preserving accuracy. On the largest scales, geometry helps describe the universe as a whole. Measurements of cosmic expansion show that space itself is stretching. Galaxies are not rushing through space away from each other. The distances between them increase because the geometry of spacetime evolves over time. This expansion is measured through redshift, a stretching of light wavelengths observed consistently across the cosmos. By studying these patterns, scientists determine the overall geometry of the universe. Current observations indicate that, on large scales, spacetime is very close to flat. This does not mean it is rigid or unchanging. It means that the average curvature balances out across vast distances. This conclusion comes from precise measurements of the cosmic microwave background and the distribution of galaxies. Even time is part of this geometry. The rate at which time passes depends on position and motion within spacetime. This effect is small in everyday life, but it becomes measurable with precise instruments. Atomic clocks placed at different altitudes tick at slightly different rates. Clocks moving at different speeds diverge predictably. These differences match geometric calculations exactly. What feels abstract becomes practical. Engineers rely on spacetime geometry to make navigation systems work. Astronomers rely on it to measure distances and masses. Physicists rely on it to test the limits of their theories. Geometry becomes a shared language connecting observation and prediction. You may find reassurance in how carefully this language is used. When geometry fails to explain an observation, scientists do not stretch it to fit. They examine the data, refine measurements, and test alternative explanations. Geometry remains tied to evidence, never drifting into assumption. There are places where geometry becomes extreme. Near very dense objects, spacetime curvature increases dramatically. Even there, the equations remain reliable within known limits. Predictions about orbits, light paths, and time dilation continue to match observation. This consistency builds confidence, not certainty, leaving room for further discovery. As your thoughts slow, the universe begins to feel orderly rather than mysterious. Geometry does not remove wonder. It channels it into understanding. Curvature, distance, and duration become gentle guides, revealing how structure shapes motion without effort or intention. The more closely scientists measure the universe, the more clearly its geometry reveals itself, suggesting that even deeper patterns may be traced with patience and care. You rest your attention on places in the universe where conditions differ greatly from those near Earth. These are not imagined locations, but environments confirmed through repeated observation. In these regions, spacetime behaves in ways that feel unfamiliar, yet remain fully consistent with established physical laws. The behavior appears strange only because everyday experience offers no comparison. One such environment surrounds neutron stars. These objects form when massive stars exhaust their fuel and collapse inward. What remains is an object with more mass than the Sun compressed into a sphere only a few tens of kilometers across. The density is extraordinary. A small amount of neutron star material would outweigh mountains on Earth. This extreme concentration of mass creates intense spacetime curvature. You can understand this curvature through observation rather than visualization. Light emitted near a neutron star loses energy as it climbs away from the strong gravitational field. This effect, called gravitational redshift, is measured directly in the spectra of radiation detected by space telescopes. The shift matches predictions made by general relativity with high accuracy. Time behaves differently as well. Clocks near a neutron star tick more slowly compared to clocks far away. This difference is not hypothetical. It is calculated precisely and confirmed indirectly through timing measurements of pulsars, which are rapidly rotating neutron stars emitting regular beams of radiation. These pulses arrive with astonishing regularity, allowing scientists to detect even tiny variations caused by spacetime effects. Black holes present even stronger conditions. They form when gravity overwhelms all other forces during collapse. The mass becomes concentrated within a region so small that spacetime curvature grows extreme. The boundary surrounding this region, known as the event horizon, marks where escape becomes impossible. Nothing unusual happens locally at this boundary. Objects crossing it do not encounter sudden forces or tearing. This behavior is predicted by theory and supported by observation. Evidence for black holes comes from multiple independent sources. Stars orbit unseen companions at high speeds, revealing the presence of massive, compact objects. X-ray emissions arise from hot material spiraling inward. Gravitational waves detected from merging black holes confirm their existence and properties. These signals match detailed calculations exactly, leaving little room for alternative explanations. In all these cases, spacetime does not break. Curves smoothly, even when curvature becomes intense. The equations describing this behavior remain valid until reaching conditions where measurements are no longer possible. This distinction matters. Scientists differentiate carefully between what is unknown and what is unsupported. Where data ends, conclusions pause. Another environment where spacetime behaves unusually lies in the early universe. Observations of the cosmic microwave background reveal patterns imprinted when the universe was young, hot, and dense. Tiny variations in temperature and density provide a snapshot of spacetime conditions billions of years ago. These measurements are consistent across independent missions and instruments. The expansion of the universe also reflects unusual spacetime behavior. Space itself increases in scale over time. This expansion is measured through redshift and distance relationships among galaxies. The effect becomes more pronounced at greater distances, indicating that spacetime evolves. Yet this evolution follows well-defined equations that match observation across vast ranges. You may notice a common theme. Strangeness does not imply unpredictability. Each unusual behavior is quantified, measured, and confirmed. Spacetime responds to mass and energy according to precise rules. Even when those responses feel extreme, they remain orderly. Gravitational waves provide another window into this behavior. When massive objects accelerate, spacetime disturbances propagate outward. These waves stretch and compress distances by tiny amounts. Detectors on Earth measure these changes directly. The signals carry information about distant events, allowing scientists to confirm how spacetime behaves under rapid, energetic motion. These waves pass through Earth without causing damage. They demonstrate flexibility rather than fragility. Spacetime accommodates motion and energy without tearing. This resilience is essential. It allows the universe to remain stable over billions of years. You may also consider how scientists approach these environments. No single observation stands alone. Results are cross-checked using different methods and instruments. Predictions are tested repeatedly. Confidence builds slowly, supported by consistency rather than surprise. Where predictions and measurements align, understanding deepens. Where they diverge, caution prevails. Scientists resist dramatic interpretation. Instead, they refine instruments, improve models, and gather more data. This careful approach keeps knowledge grounded. As your thoughts slow, these extreme regions feel less threatening and more instructive. They are natural laboratories, revealing how spacetime behaves under conditions far beyond everyday experience. They do not suggest instability. They demonstrate robustness. Even in the presence of enormous gravity, spacetime maintains coherence. Motion follows defined paths. Light behaves predictably. Time shifts in calculable ways. The universe remains governed by relationships that hold across scale and intensity. There are still unanswered questions. At the deepest levels of collapse, current theories reach limits. These limits mark where understanding ends, not where reality dissolves. They invite further study without overturning what is already known. You rest with the knowledge that spacetime has been tested in some of the most extreme environments accessible to observation. Each test reinforces its reliability while hinting at deeper layers of structure not yet fully described. You allow your attention to rest on a subtle idea, one that takes time to feel comfortable. Spacetime, though stable and structured, is not perfectly still. When massive objects move in certain ways, especially when they accelerate, spacetime responds. This response does not appear as damage or disruption. It appears as a gentle disturbance that travels outward, carrying information across vast distances. Scientists call these disturbances gravitational waves. The idea emerges directly from general relativity. If mass and energy shape spacetime, then changing distributions of mass and energy must also change that shape. When objects accelerate unevenly, especially in pairs, spacetime cannot adjust instantaneously everywhere. Instead, the adjustment spreads outward at the speed of light. This spreading change is what a gravitational wave is. For decades, gravitational waves remain a prediction rather than a measurement. Not because they are doubted, but because they are extremely subtle. By the time they reach Earth, even those produced by violent cosmic events cause changes smaller than the width of an atomic nucleus. Detecting them requires extraordinary precision and patience. That precision arrives with instruments designed specifically for this purpose. Facilities like LIGO and Virgo use long tunnels with laser beams traveling back and forth between mirrors. When a gravitational wave passes through Earth, spacetime itself stretches in one direction and compresses in another. The distance between the mirrors changes slightly. Lasers record this change as an interference pattern that can be measured and analyzed. The first direct detection occurs in 2015. The signal comes from two black holes spiraling together more than 1 billion light-years away. The shape of the signal matches predictions exactly. Its frequency, amplitude, and timing align with calculations made using general relativity. Independent detectors record the same event, confirming it is real. Since then, many additional detections follow. Some involve black hole mergers. Others involve neutron stars colliding. Each detection adds confidence. The signals are consistent. The interpretations are cautious. No observation suggests tearing, rupture, or instability in spacetime. Instead, spacetime behaves like a flexible structure, capable of carrying waves without harm. You may notice how carefully scientists describe these events. They do not say spacetime is damaged. They say it oscillates. Distances increase and decrease slightly, then return to their original values. The effect passes through Earth without leaving a trace. Buildings, oceans, and bodies remain unchanged. Only the instruments notice. Gravitational waves also carry information that cannot be obtained in other ways. They reveal masses, distances, and motions of objects that emit little or no light. They confirm the existence of black holes and test how gravity behaves under extreme conditions. Every successful match between signal and prediction reinforces the geometric description of spacetime. Time plays an essential role here as well. The timing of wave arrival at different detectors allows scientists to locate the source in the sky. Differences of milliseconds matter. This sensitivity shows how stable and predictable spacetime remains even while transmitting waves across the universe. You might expect such disturbances to accumulate or weaken spacetime over time. Observations show no such effect. The universe has hosted countless energetic events over billions of years. Spacetime continues to function consistently. Waves pass, spacetime settles, and structure remains intact. The language of waves is precise. A wave is not a crack. It does not imply separation. It implies motion within continuity. Ocean waves move water without splitting the ocean. Gravitational waves move spacetime without breaking it. This distinction is essential and supported by every measurement so far. Even the energy carried by these waves behaves predictably. It can be calculated and compared with the energy lost by orbiting objects. Pulsars in binary systems slow their orbits exactly as predicted by gravitational wave emission. This indirect evidence appears decades before direct detection, strengthening confidence long before instruments confirm it. You may feel how quietly convincing this body of evidence is. No single observation demands belief. Many observations together form a stable picture. Spacetime responds dynamically, yet remains whole. The detection of gravitational waves does not reveal weakness in the universe. It reveals communication. Events far away leave measurable imprints here. Spacetime connects regions separated by unimaginable distances through lawful behavior. As your breathing slows, the idea becomes gentle rather than dramatic. Waves pass. Distances change briefly. Order returns. The universe continues, shaped by rules that hold even under the most energetic conditions. You let your awareness rest on the framework of general relativity, feeling its equations like quiet guidelines for motion, gravity, and time. This theory has passed countless tests, from the bending of starlight to the slowing of clocks in orbit. Yet even the most reliable theory has boundaries, and you explore them gently. These limits are not weaknesses. They are well-defined areas where known physics reaches the edge of current understanding. One boundary lies within black holes. The center of a black hole, the singularity, represents a point where density becomes immense and curvature extreme. Equations predict this point mathematically, but observation cannot reach it directly. It is not a failure. It is a defined region beyond which measurements cannot penetrate. Scientists describe what happens outside the event horizon with confidence. They describe what approaches it with equations. What occurs precisely at the singularity remains unmeasured. Another extreme occurs in the earliest universe. General relativity describes how spacetime evolves over time. When extrapolated to the first fractions of a second after the Big Bang, energy densities become enormous. Temperatures are extraordinarily high. The equations indicate conditions where quantum effects must dominate. General relativity does not fail. It simply does not include quantum phenomena. Physicists recognize this boundary with careful precision. Even at these extremes, the theory remains predictive outside the limits. The cosmic microwave background, a faint glow of ancient radiation, matches predictions about expansion and geometry. Gravitational lensing behaves exactly as calculated. Planetary orbits continue to conform. No observation contradicts the equations within the tested range. Limits are boundaries, not contradictions. You may notice how this careful definition maintains trust in the theory. Scientists do not speculate wildly about what happens inside a singularity or at infinite density. Instead, they focus on measurable consequences outside those boundaries. The precision of this focus allows understanding to grow while avoiding error. There are situations where extreme density and motion approach limits of relativity. Neutron stars, rapidly rotating and dense, create strong curvature. Yet the equations continue to match observation. Material inside neutron stars remains opaque to direct measurement, but gravitational effects and radiation provide indirect confirmation. This combination of prediction and measurement reinforces confidence in the theory, while clearly marking regions where it cannot be fully tested. Time dilation near massive objects continues to operate predictably. Atomic clocks in high gravity run more slowly than clocks far away. Light curves around dense objects, bending as predicted. These phenomena persist across observations, showing no anomalies that suggest a breakdown of the theory in accessible regions. You can imagine how carefully physicists analyze data in extreme contexts. Every measurement includes error margins, calibration adjustments, and cross-checks with independent instruments. When deviations occur, scientists first investigate measurement limits, not physical failure. Only persistent, reproducible inconsistencies might suggest a need for theoretical adjustment. Even then, the adjustment is approached mathematically and cautiously. The concept of a limit becomes central to curiosity. Limits are not failures. They are invitations to study more deeply. Singularities, extreme curvature, and early universe conditions suggest new physics may emerge under conditions not yet observable. This new physics does not discard what is known. It extends understanding beyond established boundaries. Observational evidence continues to guide this process. Binary pulsars provide indirect measurement of gravitational wave emission, confirming predictions even under strong curvature. Large-scale structures of galaxies follow patterns consistent with general relativity. Gravitational lensing of distant clusters aligns with calculated curvature. No observed phenomenon yet contradicts the theory within the measurable domain. Mathematical consistency is part of this calm framework. Equations do not produce random results. They respond logically to input, whether describing planetary orbits or the merger of black holes. When results indicate extreme values, they do so systematically, revealing predictable consequences rather than unpredictability. Even as the universe grows denser or hotter, as in the cores of collapsing stars or during early expansion, the equations provide clear predictions up to their applicable range. Beyond that, physicists acknowledge uncertainty. This humility is part of the rigor. Scientific knowledge is cumulative, and limits define where accumulation must pause. Technology illustrates these boundaries as well. Satellite navigation relies on relativistic corrections, precise and predictable. High-energy particle experiments reach limits approaching those found in extreme cosmic events. Yet the corrections, calculations, and measurements all reinforce the same theory, showing it continues to hold under varied, practical, and extreme conditions. You may reflect on the elegance of this approach. A theory can be highly successful, widely confirmed, and still clearly bounded. The awareness of limits is not unsettling. It is reassuring. It shows that scientific understanding is not blind belief, but a disciplined mapping of what can be observed, measured, and calculated. Curiosity thrives within these boundaries because they define where questions remain open. The precision of general relativity allows gentle confidence. You can rely on its predictions in known contexts, from orbits to time dilation to the bending of light. Where extremes occur, scientists approach them with caution, acknowledging both the power and the boundary of the theory. This careful attention ensures that every statement about spacetime remains grounded, verifiable, and measurable. The interplay of curvature, energy, and motion demonstrates spacetime stability. Even under extreme conditions approaching theoretical limits, the universe does not behave chaotically. Orbits remain orderly, light continues its predictable path, and time shifts remain calculable. This reliability forms a quiet rhythm you can follow with attention and calm. You may notice how limits also guide exploration. Where equations reach boundaries, new experiments, new observations, and new technologies are designed to probe further. The unknown is mapped slowly and deliberately. Each new measurement extends the domain of confirmed understanding without discarding what has already been verified. The concept of limits is central to scientific curiosity. They define where imagination can explore hypotheses safely, constrained by evidence. Spacetime continues to behave predictably outside these limits, and within them it invites study. Boundaries become a gentle form of guidance rather than a source of uncertainty. As your thoughts settle, the framework of spacetime feels simultaneously vast and reliable. Limits exist, but they mark edges of observation rather than collapse of understanding. Each region behaves according to precise laws, yet hints at deeper structures awaiting careful exploration. You let your attention shift downward to the scale of the very small. This is the domain of quantum physics, where the familiar rules of classical motion give way to behavior that is both measured and probabilistic. Particles appear as points in some experiments and waves in others, yet every observation follows predictable patterns that have been tested repeatedly. You may find it reassuring that these rules are not speculation. They are measured, confirmed, and consistent. At this scale, energy comes in discrete packets called quanta. Light, for instance, behaves as both a wave and a particle depending on how it is measured. Photons carry energy in precise amounts, and the probability of detecting one at a specific location can be calculated accurately. Experiments such as the double-slit experiment reveal interference patterns that match the predictions of quantum mechanics exactly. These patterns are not random. They reveal a hidden structure of probabilities governing the behavior of particles. Quantum mechanics also describes the fundamental particles that compose matter. Electrons, quarks, and neutrinos exist with properties measured to extraordinary precision. Their masses, charges, and spins are constants of nature, determined through experiments that can be repeated in different laboratories anywhere in the world. These measurements confirm that quantum physics is reliable, even when individual particles behave unpredictably in isolation. The mathematics of quantum physics provides exact probabilities for measurement outcomes. It does not claim certainty for single events, but it predicts averages and distributions with incredible accuracy. Atomic spectra, chemical reactions, and subatomic interactions all conform to these rules. Engineers and physicists rely on them to build lasers, semiconductors, and particle accelerators. The results are predictable, functional, and repeatedly verified. One of the key features of this realm is uncertainty. Certain properties, such as position and momentum, cannot be simultaneously known with perfect precision. This is not due to measurement error, but a fundamental property of nature. The Heisenberg uncertainty principle quantifies this limit. Despite this inherent uncertainty, repeated measurements produce consistent statistical patterns that allow reliable prediction at the level of probabilities. Quantum entanglement introduces another subtle feature. Pairs of particles can be connected such that the state of one instantly correlates with the state of the other, even when separated by vast distances. This phenomenon has been confirmed experimentally through violations of Bell's inequalities and repeated testing over decades. While it challenges intuition, it does not break causality or allow faster-than-light communication. Instead, it reflects a deeper, measurable structure of reality. Experiments with quantum systems are performed under controlled conditions, often at extremely low temperatures or in high vacuums. These settings ensure that interactions with the environment do not obscure the delicate patterns that quantum theory predicts. Results consistently match expectations. Reproducibility is a cornerstone. The careful design of experiments ensures that observations are not artifacts but genuine features of quantum systems. Even though quantum physics describes behaviors that are invisible to the naked eye, it has observable consequences at larger scales. Semiconductors rely on electron energy levels. Lasers depend on precise quantum transitions. Magnetic resonance imaging relies on nuclear spins. In all these technologies, quantum principles guide predictable outcomes. These applications show that quantum physics is not abstract. It is practical, measurable, and reliable. You may notice that quantum mechanics and general relativity describe very different regimes. Relativity governs large-scale spacetime and gravitation, while quantum mechanics governs particles and interactions at the smallest scales. They are not in contradiction. They describe different phenomena. The challenge arises when attempting to unify them, but this does not invalidate the observations in either domain. The domain of the very small also introduces the concept of vacuum fluctuations. Even empty space is not empty. Tiny, temporary particle-antiparticle pairs appear and disappear spontaneously. These fluctuations have measurable effects, such as the Casimir effect, where plates placed very close together experience a slight force due to the quantum vacuum. Observing these effects requires precision instruments, yet the measurements match predictions. Quantum mechanics relies heavily on probability, but it does not mean chaos. Patterns emerge consistently when systems are studied repeatedly. Atomic decay rates, interference patterns, and particle scattering all conform to calculated probabilities. Each experiment, repeated carefully, reinforces confidence in the underlying laws. You may reflect on the contrast between predictability and uncertainty. In classical terms, motion is deterministic with exact outcomes. In quantum terms, outcomes are probabilistic, yet the probabilities themselves are precise and reliable. This duality is part of the structure of the universe, offering both limits and possibilities. Measurement is central in this framework. The act of observing a quantum system affects the outcome in a predictable way. Scientists account for this in every experiment, ensuring that predictions and measurements align. The process is meticulous and replicable, reinforcing the calm reliability of the theory despite counterintuitive results. You can rest in the knowledge that quantum mechanics is tested through countless experiments over decades, and its principles underpin much of modern technology. Its rules are precise, consistent, and experimentally confirmed. Even behaviors that feel unusual or uncertain follow strict mathematical and observational laws. The domain of the very small hints at a deeper structure beneath the fabric of spacetime. While general relativity describes smooth curvature and motion, quantum mechanics reveals granularity, probabilities, and fluctuation. Both perspectives are measured, verified, and complementary, each providing a stable foundation for understanding phenomena within its scale. As your thoughts slow, the small-scale universe feels less mysterious and more structured. Particles follow predictable patterns, probabilities unfold reliably, and the universe operates according to rules confirmed through repeated measurement. Observing these behaviors encourages curiosity about how these microscopic principles might connect with the larger geometry of spacetime you have already explored. You begin by attending to the language that scientists use when describing spacetime. Words carry precision in physics. When an article suggests a crack in spacetime, it does not mean a tear or rupture. Instead, it refers to small, carefully measured inconsistencies or tensions between theory and observation. Understanding this distinction requires slowing down and considering how science works. Science is built on measurement, repetition, and peer review. When data diverges from prediction, researchers do not announce the universe is broken. They examine instruments, check calculations, and verify assumptions. Only when anomalies persist under careful scrutiny do they raise questions about the theoretical framework. These questions are discussed cautiously, framed in probabilities and possibilities, not certainties. The idea of a crack often arises in regions where general relativity and quantum mechanics approach each other. Both theories are extraordinarily successful within their domains, but they describe very different phenomena. Gravity governs spacetime on large scales, while quantum mechanics governs subatomic interactions. Reconciling them is a challenge because observations of one domain may hint at effects that the other does not predict. This does not indicate failure. It highlights boundaries and opportunities for investigation. One example appears in measurements of the universe's expansion rate. Observations using supernovae, cosmic microwave background, and gravitational lensing yield slightly different results for the Hubble constant. The differences are small, measured in percentages, but statistically significant. Scientists discuss whether these discrepancies hint at new physics, subtle measurement errors, or aspects of spacetime behavior not yet fully understood. They do so carefully with precise calculations and repeated measurements. Another context arises in high-energy astrophysics. Observations of cosmic rays and gamma-ray bursts occasionally challenge expectations. Detected patterns can be difficult to reconcile fully with current models. Physicists explore whether they indicate extreme conditions, instrumental limitations, or previously unnoticed effects. The word crack in popular discussions refers to these very specific tensions rather than a literal rift. The language used in scientific papers is deliberate. Authors distinguish between anomalies, uncertainties, and genuine contradictions. Each term has a precise meaning. An anomaly is an observation not yet explained by existing models. Uncertainty is a quantified limitation of measurement. A contradiction would occur if repeated measurements consistently defy well-tested predictions. So far, no measurement has produced a contradiction that invalidates general relativity or quantum mechanics. Instead, researchers identify points where refinement is possible. Laboratory experiments also contribute. High-precision measurements of particle behavior, atomic transitions, and gravitational effects sometimes reveal subtle discrepancies with predictions. These discrepancies are meticulously examined. They may lead to better understanding of experimental limitations, improved models, or insights into new phenomena. At every step, evidence is prioritized over speculation. When discussing a crack, scientists also consider theoretical models. Models predict how spacetime behaves under known conditions. If a model predicts an effect that is not observed, or if an observation exceeds prediction, this may signal a domain where the model requires extension. The term crack thus functions as a placeholder for areas of curiosity, where theories intersect with high-precision data. It does not imply instability or breakdown of the underlying spacetime fabric. You may find reassurance in the iterative nature of this process. Nothing in current evidence suggests spacetime is fragile or collapsing. Every observation is tested against multiple instruments and cross-checked with independent calculations. Anomalies are investigated over years, sometimes decades, before any conclusion is drawn. This careful approach ensures reliability. Statistical analysis plays a crucial role. Scientists quantify the likelihood that an observed deviation could arise from chance or error. Only anomalies with a high degree of confidence prompt discussion about potential theoretical implications. The thresholds are deliberately conservative, ensuring that only genuinely unusual results attract attention. This conservatism helps maintain trust in what is already well understood. Another example involves gravitational waves. The signals detected from colliding black holes and neutron stars match predictions extremely closely. Minor variations in amplitude or frequency are examined to refine models, not to suggest cracks. Even the smallest deviations are interpreted cautiously, always in the context of measurement error and signal noise. The media sometimes simplifies this careful language, using terms like crack or tear to attract attention. Scientists reading the same reports recognize the distinction. They continue to focus on data, reproducibility, and theoretical consistency. The public interpretation does not change the underlying stability of spacetime or the precision of experimental results. You can appreciate the patience required in this work. Researchers often repeat measurements hundreds or thousands of times, compare instruments across continents, and consult extensive datasets. This slow accumulation of evidence allows the community to separate real anomalies from artifacts. The process is deliberate, methodical, and reassuringly precise. The concept of a crack also illustrates the humility inherent in science. Scientists acknowledge what they do not yet know without claiming that the universe itself is unstable. They frame unknowns carefully, clearly defining boundaries between measured facts, extrapolated predictions, and theoretical speculation. This approach builds understanding gradually, without creating unnecessary concern. You may notice a consistent theme. Spacetime is measured, modeled, and verified. Deviations are small, localized, and investigated rigorously. They are not catastrophic or chaotic. Each anomaly or tension is an invitation to look closer, refine instruments, or improve models. The stability of spacetime is confirmed repeatedly, while the boundaries of knowledge remain open for careful study. Even the most extreme astronomical events, like black hole mergers or neutron star collisions, confirm the integrity of spacetime. Measurements of gravitational waves show smooth, predictable behavior. Light curves, timing, and radiation all follow precise rules. The anomalies observed at the edges of measurement are subtle and quantified, never implying a literal rupture. Scientific language, mathematics, and instrumentation work together to create confidence. Observations are compared globally, predictions are modeled rigorously, and uncertainties are acknowledged. The term crack represents a defined space for curiosity, where precision, patience, and careful measurement converge. As your thoughts slow, you recognize that a crack is not a fracture. It is a signpost pointing toward questions, gaps, and potential discoveries. The universe continues to behave reliably, offering subtle puzzles that invite careful attention and gentle exploration. You begin by resting in the quiet space of observation, where data is collected with precision and care. Observing the universe is not a matter of casual looking. It requires instruments designed for sensitivity, stability, and repeatability. Telescopes capture light from billions of galaxies. Detectors measure gravitational waves. Satellites record the faint glow of the cosmic microwave background. Every measurement is a small step toward understanding. One of the first examples is the measurement of the universe's expansion rate. Scientists rely on a variety of methods. Observations of distant supernovae provide one estimate. Measurements of the cosmic microwave background provide another. Each method is independent, relying on distinct instruments, analysis techniques, and assumptions. The results are not identical. Differences are small, but measurable and statistically significant. These discrepancies become the focus of discussion and careful examination. You notice how scientists respond. They do not panic or claim a crisis. Instead, they analyze uncertainties, calibrate instruments, and compare datasets. Each group calculates the confidence intervals for their measurements. They assess the probability that differences arise from chance, instrumental error, or underlying physics. This statistical care allows even small tensions to be evaluated calmly. Beyond cosmic expansion, other observations spark careful discussion. Light from distant stars is bent by massive galaxies, a phenomenon called gravitational lensing. Multiple teams measure lensing patterns to infer mass distributions. Slight differences appear between analyses. These differences are discussed openly in scientific literature, often leading to refinements in methodology or data handling. The process is iterative, precise, and collaborative. Pulsar timing provides another example. Neutron stars emit regular pulses of radiation, sometimes with millisecond precision. Astronomers use these pulses to detect gravitational waves or to measure orbital dynamics. Differences in observed arrival times can indicate unknown effects or refine existing models. Each anomaly is documented, analyzed, and shared with the community. Transparency ensures that no single interpretation dominates prematurely. You can appreciate the careful patience involved. Every dataset carries error bars, uncertainty margins, and limitations. Scientists respect these boundaries. They do not overstate results. Even when observations appear inconsistent, the response is methodical. Review, recalculate, replicate. Observational disagreement is treated as a clue, not a contradiction. This approach strengthens confidence in the results that survive scrutiny. Laboratory experiments also contribute to these discussions. Precision measurements of atomic transitions, particle masses, or energy levels sometimes reveal small deviations from predictions. Physicists do not immediately attribute these to new physics. They check calibration, assess environmental factors, and consider systematic errors. Only after repeated, independent measurements do they contemplate the possibility of a genuine anomaly. This patience maintains rigor. Observations in high-energy astrophysics illustrate similar care. Gamma-ray bursts and cosmic rays are measured across multiple detectors. Differences in signal intensity or timing may arise due to detector sensitivity, atmospheric interference, or statistical noise. Teams analyze these differences, quantify uncertainties, and publish their methods for review. The resulting dialogue is not about drama. It is about precision. You can notice a recurring theme. Observation is an active, iterative process. Disagreement between measurements is expected and managed. It is not a sign that nature is unstable. It is a signal that measurement techniques, assumptions, or conditions may need closer attention. This iterative refinement allows science to progress slowly and reliably. Large-scale surveys, such as those mapping the distribution of galaxies, also show small tensions. Different telescopes or surveys produce slightly varying results for density fluctuations or cosmic structures. Scientists assess these differences statistically, often using simulations to model observational limitations. The careful comparison between datasets strengthens conclusions and highlights areas for further study. Observations also intersect with theoretical expectations. Predictions made by general relativity, quantum mechanics, and cosmology are tested against measured data. Discrepancies that persist beyond experimental uncertainty draw attention to possible extensions or refinements in theory. These moments are exciting, yet handled with caution and rigor. The universe provides hints, not certainties. You may notice how collaborative this process is. Data is shared openly, methods are published, and results are scrutinized by independent teams. Peer review ensures that findings are verified before gaining wide acceptance. Scientific discussion is deliberate, slow, and grounded in evidence. Even when differences appear, the conversation remains methodical, aimed at clarity rather than sensationalism. Astronomical observations sometimes reveal effects that were not anticipated, such as the discovery of dark energy. The faint acceleration of cosmic expansion was detected through repeated supernova observations and analyzed statistically. Scientists did not jump to dramatic conclusions. They confirmed results across independent studies and developed models consistent with existing physics. This measured response exemplifies how careful observation can lead to profound yet reliable insight. Even small observational discrepancies are treated as opportunities rather than crises. They are logged, analyzed, and discussed with explicit acknowledgement of limitations. Uncertainty is quantified, and instruments are recalibrated. Observations build upon one another, gradually refining knowledge while maintaining accuracy. The universe is explored patiently, and every minor tension is an invitation to improve understanding. You may notice how this approach contrasts with casual interpretation. Public reports sometimes exaggerate the significance of minor discrepancies, but the scientific community maintains focus on measurement, replication, and analysis. Disagreement is a tool for refinement, not a cause for alarm. Observational data also interacts across scales. Measurements of local phenomena, such as pulsar timing, connect to cosmic-scale observations like expansion rates. Consistency across scales reinforces confidence, while small tensions guide further study. This layered structure demonstrates the resilience of the scientific method and the reliability of spacetime observations. You can feel how small differences between datasets do not destabilize understanding. They are indicators of where instruments or models may need refinement. They guide attention without undermining the consistent framework established over decades. Observation remains the cornerstone of knowledge, approached with care, patience, and precision. Even subtle discrepancies are valuable. They encourage repeated measurement, verification, and methodological improvement. Scientific strength arises from this process. Debate is not a weakness but a sign that the system self-corrects and that conclusions are built on solid evidence. Observation, analysis, and discussion work together to refine knowledge gently and reliably. As your mind settles, you recognize that the universe communicates in patterns, signals, and subtle differences. Each measurement, each tension between results, is a whisper of information. These whispers are examined patiently, analyzed mathematically, and interpreted collectively. The process reinforces that disagreement, when handled carefully, strengthens confidence in what is measured and understood. You begin by noticing that every observation depends on the tools used to make it. Telescopes, particle detectors, satellites, and clocks are not perfect. They have finite precision and sensitivity. Even the most advanced instruments carry inherent limitations. Recognizing these limits is not a flaw, it is a foundational part of understanding the universe accurately. Calibration is the first step. Instruments are aligned and tested against known standards to ensure that measurements are accurate. For example, atomic clocks are compared with other clocks to maintain time standards. Telescopes are pointed at reference stars to confirm alignment. Detectors are exposed to controlled sources to ensure response accuracy. These procedures reduce systematic errors, allowing scientists to trust the measurements they record. Noise is another unavoidable factor. Every instrument records signals that contain both the desired information and background fluctuations. In gravitational wave detectors, laser interferometers are affected by seismic vibrations, thermal variations, and even passing traffic. Particle detectors register cosmic rays and electronic interference. Scientists quantify noise carefully and design experiments to minimize it, but they also account for its presence in all analyses. Uncertainty is a natural outcome of both noise and finite precision. No measurement can be infinitely exact. Instead, scientists express results with error bars or confidence intervals, indicating the range within which the true value likely lies. A distance measurement might be stated as 1.000 plus or minus 0.002 meters. A redshift measurement might carry a tiny statistical margin. These notations are not imperfections. They are honest expressions of what is known and how well it is known. Some measurements push instruments to their absolute limits. Observing a faint galaxy billions of light-years away requires collecting tiny amounts of light over long periods. Detecting a neutrino involves recording one rare particle among trillions passing through a detector every second. Measuring minuscule spacetime distortions demands interferometers capable of detecting movements smaller than the width of a proton. These extraordinary feats rely on careful design, calibration, and understanding of noise and uncertainty. Scientists also perform repeated measurements to reduce uncertainty. Individual readings may fluctuate due to statistical variations. Repetition allows averages to approach the true value and provides a measure of reliability. Large datasets, often collected over years, help distinguish genuine signals from random fluctuations or transient anomalies. Cross-checking with independent instruments adds another layer of confidence. Observatories located in different countries can record the same event. Particle experiments in separate laboratories can measure the same phenomenon using different techniques. When independent measurements agree, confidence rises. When they diverge, scientists investigate, recalibrate, and refine methods. This careful redundancy prevents hasty conclusions. You notice how the limitations of instruments also guide interpretation. When an unexpected signal appears, scientists first consider whether it could be caused by instrumental effects. Could a detector glitch, thermal fluctuation, or calibration error explain the observation? Only after these possibilities are systematically ruled out do researchers explore whether the signal represents a real physical phenomenon. This cautious approach preserves accuracy. Measurement limits also explain why extraordinary claims require extraordinary care. Observing a subtle feature in spacetime, a faint particle signal, or a tiny difference in cosmic expansion is not sufficient by itself. Scientists demand repeated detection, confirmation with multiple methods, and rigorous statistical analysis. The universe is not prone to deception, but instruments can be. Careful attention protects conclusions from error. Instruments evolve over time, becoming more precise and sensitive. Laser interferometers improve, particle detectors increase their resolution, and telescopes gather more light with less noise. Each upgrade opens a new window into phenomena that were previously inaccessible. Yet each new instrument is calibrated, tested, and validated before results are interpreted. Advancement in capability is matched by rigorous understanding of limits. Data processing is another essential aspect. Raw measurements often require filtering, correction, and analysis. Noise reduction, background subtraction, and signal extraction are applied using standardized, tested methods. Scientists verify that processing does not introduce artifacts or bias. Transparency in data treatment ensures that conclusions remain reliable, even when signals are subtle or near the detection threshold. You may notice that precision is relative. What is sufficient for one measurement may be insufficient for another. Detecting a nearby star's orbit requires much less sensitivity than detecting a faint galaxy at high redshift. Gravitational wave detection requires instruments at the edge of technological capability. Awareness of relative precision allows researchers to design experiments appropriate for the scale of the phenomenon. Limits of measurement also shape scientific discourse. Small anomalies often lead to debate, as scientists consider whether they represent true effects or instrumental limitations. Every claim is examined with awareness of what the instrument can actually resolve. This discipline ensures that speculation is grounded in fact and that excitement does not overshadow reliability. Error bars and confidence intervals are not merely symbols, they are expressions of scientific honesty. They communicate what is known and, equally importantly, what remains uncertain. Every measurement carries these qualifiers, reminding researchers and readers alike that science progresses incrementally through verification, replication, and refinement. You can feel the rhythm of this careful work. Observations, calibrations, repetitions, and cross-checks form a steady pattern. Each step reduces uncertainty, enhances precision, and builds confidence. The process is deliberate, meticulous, and deeply reassuring. It demonstrates that our understanding of the universe grows reliably, guided by the capabilities of instruments and the care of those who use them. Even when measurements reach the limits of current instruments, scientists learn from them. Null results, constraints, and upper or lower bounds inform theory and guide the design of future experiments. These limits are not failures. They are markers of what is achievable with present technology, and signposts pointing toward improvement. You may notice how measurement care interacts with observation itself. Detecting gravitational waves, Faint starlight or rare particle interactions requires both technological sophistication and disciplined methodology. The subtlety of signals demands patience, repetition, and cross-validation. Each tiny measurement contributes to a larger, consistent picture of the universe. The understanding of instrumental limits also reinforces trust in scientific debate. When different teams obtain slightly different results, the discussion is framed by knowledge of what instruments can resolve. Researchers adjust expectations, refine methods, and report results with clarity. Small disagreements are understood as natural consequences of measurement boundaries rather than instability in the phenomena themselves. You may feel how extraordinary precision requires extraordinary caution. Measuring spacetime distortions smaller than a proton, detecting a single neutrino among trillions, or identifying slight differences in expansion rate demands that every detail calibration, noise, uncertainty, and error analysis is accounted for. This diligence ensures that what is measured reflects the universe itself, not the quirks of the instrument. Ultimately, instrument precision and limits are inseparable from scientific reliability. Each detection, each measurement, each refinement strengthens understanding because it is undertaken with full awareness of what can and cannot be known. Instruments do not lie, but their limitations are always acknowledged, respected, and accounted for. You begin by noticing that data alone is rarely enough to provide a complete understanding of the universe. Observations, while precise, often reveal patterns without immediately explaining their causes. Theoretical models serve as structured frameworks to interpret these patterns. A model is a set of mathematical relationships and assumptions that aims to reproduce observed behavior and predict outcomes under new conditions. Building a model starts with careful observation. Scientists examine what is known, orbital dynamics, cosmic microwave background fluctuations, gravitational waves, particle interactions, and identify regularities. They then construct equations and principles that describe these regularities consistently. A model is never an assertion of absolute truth. It is a tool to organize knowledge, test predictions, and explore consequences. Models must conform to all existing measurements. A proposed model for spacetime behavior, for example, cannot contradict verified observations of gravitational lensing, planetary motion, or the bending of light. Each prediction is compared with known data. If discrepancies arise, the model must be refined or discarded. This ensures that theoretical innovation remains grounded in empirical reality. Testing a model involves predicting observations not yet measured or explaining known anomalies. When new data arrives, it is compared to the model's predictions. If the model succeeds, confidence grows. If it fails, scientists carefully examine whether the failure is due to incorrect assumptions, oversimplifications, or experimental error. Only after rigorous evaluation is a model considered insufficient. Simplification is part of the process. Models often focus on key variables while temporarily ignoring secondary effects to gain clarity. For instance, planetary motion models may initially neglect minor gravitational perturbations from distant stars. Over time, refinements incorporate these effects, increasing accuracy without compromising the original framework. This incremental approach balances tractability and realism. Predictions are central. A model must produce expectations that can be measured. If a theoretical description of spacetime predicts a certain gravitational wave pattern, detectors can be configured to test it. Observations either confirm the prediction, providing support for the model, or reveal deviations that require revision. Predictive power is a measure of a model's strength, but it is always subject to empirical verification. Models also provide insight into unobservable phenomena. Black holes, for example, cannot be directly examined inside the event horizon. Theoretical models describe their behavior based on the effects they have on surrounding matter and light. Observations of accretion disks, relativistic jets, and orbital motion confirm the predictions, showing how a model extends understanding while remaining anchored in measurable effects. You may notice that the process is iterative. Models evolve gradually, responding to new evidence. Refinements adjust parameters, incorporate previously neglected interactions, and extend domains of applicability. Entirely new models emerge when old frameworks fail to explain repeated, verified observations. Each step is deliberate, guided by evidence, not imagination. Precision in modeling is essential. Small errors in assumptions can lead to large deviations in predictions, particularly in complex systems such as galaxies, neutron stars, or spacetime curvature near massive objects. Scientists use careful calculations, computational simulations, and cross-validation to ensure models remain internally consistent and externally accurate. You may also observe that multiple models can coexist temporarily. Different approaches may explain the same phenomena from slightly varied perspectives. For instance, alternative cosmological models may differ in assumptions about dark energy or dark matter. Each is evaluated against all available evidence. Over time, models that fail to match observations are discarded or modified, leaving the ones that reliably describe reality. Models must be falsifiable. A useful model makes predictions that could, in principle, be proven wrong through observation. This is a defining feature of scientific methodology. Without falsifiability, a model cannot be tested or refined, and its reliability remains uncertain. By constructing predictions that can be challenged, scientists ensure that theoretical frameworks remain grounded in measurable reality. You notice how restraint is built into modeling. Extraordinary claims, such as unusual spacetime behavior, require extraordinary alignment with observation. A new model cannot simply propose a dramatic effect without reproducing all existing measurements. This ensures that imagination does not overrule evidence, and that theoretical exploration proceeds methodically. Computational models play an increasingly important role. Simulations of galaxy formation, gravitational wave emission, or particle interactions allow scientists to explore complex scenarios that are difficult or impossible to replicate experimentally. These simulations are constructed from validated theoretical principles, providing a virtual laboratory in which predictions can be tested and refined. Collaboration strengthens the reliability of models. Independent teams construct models, compare results, and test predictions against diverse datasets. Peer review ensures that assumptions, methods, and conclusions are examined thoroughly. Only when a model withstands scrutiny across multiple perspectives does it gain broader acceptance. You may feel the careful balance between creativity and discipline. Models allow scientists to explore the universe's behavior, imagine outcomes under different conditions, and propose mechanisms for observed phenomena. At the same time, every model is constrained by evidence, tested repeatedly, and revised cautiously. The process exemplifies the slow accumulation of knowledge. Theoretical models also help identify gaps in observation. If a model predicts behavior that cannot yet be measured, it guides future experiments. Scientists design instruments and observational campaigns to test these predictions, expanding understanding systematically. Models thus provide both interpretation of known data and direction for new exploration. Even when anomalies arise, the discipline of modeling ensures that explanations are carefully evaluated. Discrepancies do not automatically signal a flaw in reality. They indicate areas where assumptions, simplifications, or experimental uncertainties may play a role. The interplay between observation and model refinement maintains rigor and clarity. You may notice how models are intertwined with measurement limits. The precision of instruments sets the scale at which predictions can be tested. Small deviations must be interpreted within the context of these limits. Models, therefore, are always evaluated alongside an understanding of observational capacity, ensuring conclusions are both realistic and grounded. Models provide a stable framework for scientific curiosity. They describe complex interactions in understandable terms, guide investigation, and allow predictions that can be verified. The process is cumulative. Each refinement adds to knowledge, each failed prediction clarifies limits, and each successful prediction strengthens confidence. Scientific progress is gentle, deliberate, and precise. You can appreciate that models do not create certainty where it does not exist. They represent the best current understanding, bounded by evidence, replicable experiments, and statistical reliability. Uncertainty is acknowledged, predictions are testable, and refinement is continuous. This disciplined approach maintains calm and trust in scientific exploration. You begin by noticing that no scientific claim is accepted immediately. Observation and modeling are only the first steps. After initial findings, results enter a process of careful scrutiny known as peer review. Experts with relevant experience examine methods, calculations, and conclusions. They ask questions, suggest refinements, and check for possible errors. This process is deliberate, ensuring that findings are not accepted on impulse. Peer review is not a barrier to discovery but a safeguard. It confirms that conclusions follow logically from data and that interpretations are consistent with existing knowledge. Reviewers consider experimental design, measurement precision, statistical treatment, and clarity of reasoning. Every claim is examined for reproducibility and reliability. This deliberate pace ensures that only well-supported results gain recognition. Replication is central to validation. Independent researchers perform the same experiments or observations to confirm results. If findings can be reproduced consistently across different instruments, laboratories, or observational techniques, confidence grows. If discrepancies appear, scientists investigate, recalibrate, and refine methods. Replication transforms a single observation into robust knowledge. You notice that caution is essential when results seem extraordinary. Discoveries that suggest unusual space-time behavior, unexpected particles, or new cosmic phenomena undergo heightened scrutiny. Extraordinary claims must survive repeated analysis, cross-checking, and independent verification. Enthusiasm alone is insufficient. Evidence must be rigorous, reproducible, and consistent with known principles. Statistical evaluation plays a crucial role in peer review. Scientists assess the probability that results could occur by chance. Confidence intervals, error margins, and p-values are examined to determine reliability. If the statistical analysis is flawed or incomplete, reviewers request clarification, additional calculations, or further experimentation. This meticulous attention reinforces precision and prevents misinterpretation. Transparency is also critical. Researchers share methodologies, data, and assumptions openly. This allows others to verify results independently. Transparency ensures that findings are not influenced by hidden biases or unrecognized errors. Open discussion, documentation, and replication together create a stable foundation for scientific knowledge. You may notice that criticism is constructive, not adversarial. Peer reviewers aim to improve the reliability of conclusions. They point out potential confounding factors, methodological gaps, or interpretational ambiguities. This feedback is integrated into revised analyses, enhancing clarity, accuracy, and trustworthiness. The process strengthens confidence in results without undermining curiosity. Scientific journals play a key role in coordinating peer review. They provide platforms for sharing methods, data, and conclusions while coordinating evaluations by experts. Journals ensure that claims meet established standards before dissemination. Even after publication, findings remain subject to ongoing scrutiny and independent replication. Knowledge grows incrementally, grounded in collective evaluation rather than single announcements. You notice that caution extends to communication outside the scientific community. Media reports often emphasize novelty or sensational aspects. Scientists respond by highlighting limitations, uncertainty, and the need for replication. The method values measured interpretation over dramatic claims. This careful communication preserves the integrity of both the process and the understanding it produces. The peer review process is iterative. Initial submissions may be revised multiple times before acceptance. Revisions address reviewer comments, clarify methods, or correct errors. Even after publication, post-publication review continues. Letters to the editor, replication studies, and meta-analyses refine understanding. Science remains a collaborative, evolving endeavor where knowledge is strengthened through scrutiny. You can appreciate how this cautious approach maintains stability in understanding. Even small anomalies are interpreted with care. Researchers consider measurement limits, instrument precision, and statistical significance before drawing conclusions. The universe itself remains steady. It is our interpretation that is continually refined through methodical assessment. Independent verification across different groups is particularly reassuring. Experiments performed on different continents, using separate instruments, confirm consistent results. Astronomical observations, particle physics experiments, and gravitational measurements all benefit from this redundancy. Agreement among independent studies builds confidence, while differences inspire further investigation. You notice that peer review and replication also prevent premature claims from taking hold. Findings that cannot be reproduced or that rely on subtle statistical anomalies are treated cautiously. Over time, unreliable results fade, and those supported by evidence endure. This natural filtration protects the body of knowledge from accidental errors or overinterpretation. Collaboration and discussion extend beyond formal review. Conferences, workshops, and informal communications allow scientists to share insights, identify potential errors, and propose refinements. This collective evaluation forms a network of verification, ensuring that findings are robust and interpretations are carefully considered. You may feel the deliberate rhythm of this process. Observation, modeling, review, replication, and discussion form a cycle of careful validation. Each step reinforces confidence, minimizes error, and strengthens understanding. The method is slow but reliable, building certainty gradually rather than relying on immediate excitement. Ultimately, the discipline of peer review and cautious evaluation ensures that scientific claims are grounded in evidence. Knowledge is accumulated carefully, conclusions are tempered with uncertainty, and extraordinary findings are held to the highest standards. This methodical process allows you to trust what is known while remaining curious about what remains to be discovered. You can observe that the strength of science does not come from speed or sensation. It comes from precision, verification, and the willingness to question and test each claim. The system is designed to detect errors, refine understanding, and maintain reliability over time. Curiosity and rigor coexist, creating a stable, trustworthy path toward knowledge. You begin by noticing that even in areas where science is strongest, questions remain. Understanding what is not yet known is as important as knowing what is well established. Scientists define unknowns precisely, identifying the boundaries of current knowledge and clarifying where speculation begins. This careful delineation prevents confusion and ensures that curiosity is informed. One area of uncertainty involves the nature of dark matter. Observations of galaxy rotation curves, gravitational lensing, and cosmic structure require more mass than visible matter can provide. Scientists can measure its effects, yet the composition of dark matter remains unknown. Experiments with particle detectors, astronomical surveys, and collider studies search for candidates, but results are not yet conclusive. The unknown is clearly defined. We know its gravitational effects, but not its particles or interactions. Similarly, dark energy is a precise unknown. Observations indicate that the universe's expansion is accelerating. This behavior is well measured, yet the underlying cause is unidentified. The phenomenon is quantified through measurements of supernovae, cosmic microwave background fluctuations, and baryon acoustic oscillations. Scientists define the limits of understanding, specifying the observational evidence while acknowledging that the theoretical explanation is incomplete. The behavior of spacetime under extreme conditions remains a carefully circumscribed unknown. Near singularities in black holes, the combination of general relativity and quantum mechanics has not yet been fully reconciled. The equations work individually in their domains, but their union under extreme curvature is not yet solved. Researchers define these gaps explicitly, distinguishing between what can be calculated and what remains speculative. You notice that measurement limits also contribute to what is unknown. Instruments have finite sensitivity, resolution, and coverage. Subtle effects may remain undetected simply because our technology is not yet sufficient. For example, gravitational waves from certain sources may be too weak to register with current detectors. These limitations define the edge of observational knowledge, marking precisely where uncertainty lies. Another defined unknown involves the earliest moments of the universe. Observations reach back to the cosmic microwave background, around 380,000 years after the Big Bang, but conditions prior to that time are constrained primarily by models and indirect evidence. Scientists clearly specify what can be inferred, where assumptions are applied, and where empirical data does not exist. This precision maintains clarity between measured facts and modeled extrapolations. The properties of neutrinos and other elusive particles represent another well-defined frontier. Oscillation patterns, masses, and interaction probabilities are measured with increasing accuracy, yet questions remain. Experiments quantify ranges, upper limits, and probabilities, creating a precise map of what is unknown. This structured uncertainty is distinct from guesswork. It is information that guides ongoing investigation. Quantum gravity is also a clearly bounded unknown. The reconciliation of spacetime curvature with quantum field theory has not been achieved. Researchers know the constraints, such as the need for a theory that reduces to general relativity on large scales and to quantum mechanics on small scales. These requirements precisely delimit the search for new theories, keeping exploration grounded in mathematical consistency and experimental plausibility. You can see that defining unknowns involves both observation and theory. Scientists articulate what is measurable, what is inferred, and what remains unresolved. Each unknown is associated with specific conditions, quantities, or phenomena. This careful definition allows investigation to be systematic rather than speculative, providing a roadmap for future study. Observational gaps are mapped with similar rigor. Sky surveys identify regions and wavelengths where data is sparse or uncertain. Particle experiments note where detection thresholds have not yet been reached. These gaps are precisely recorded, guiding subsequent research and instrument development. Scientists know exactly where knowledge ends and investigation begins. Theoretical boundaries are also defined with care. Equations and models specify domains where predictions are valid and domains where extrapolation is uncertain. When models fail, the limitations are precisely stated rather than implied vaguely. This honesty ensures that speculation is recognized as such and that conclusions are not overstated. You notice that defining unknowns fosters curiosity rather than confusion. Clear boundaries provide focus for inquiry. Researchers prioritize questions that are tractable, measurable, and relevant to existing knowledge. The unknown becomes a structured landscape for exploration, not a void of uncertainty. Scientific communication reflects this precision. Papers, presentations, and lectures specify what is known, what is measured, and what remains unverified. Uncertainty is quantified, ranges are expressed, and assumptions are explicitly stated. Listeners and readers are guided to understand precisely where evidence ends, which cultivates informed curiosity without anxiety. Even the largest mysteries, cosmic inflation, the true nature of black hole interiors, or the potential for unknown forces, are framed with explicit boundaries. Researchers distinguish between hypotheses, models, and evidence-based conclusions. Unknowns are cataloged carefully, ensuring that speculation remains labeled and distinct from confirmed knowledge. You can observe that uncertainty is an opportunity. By defining unknowns, science identifies where future observations, experiments, and theoretical work can make meaningful contributions. Each well-characterized unknown directs attention, guiding research and instrument development to maximize insight. The precision of this approach ensures efficiency and clarity. You notice how cumulative knowledge interacts with uncertainty. The areas we do understand provide a stable framework within which the unknowns are explored. Known physics constrains possibilities, guiding hypotheses and experiments. Unknowns are approached systematically, maintaining reliability and reinforcing confidence in established understanding. Even in defining the unknown, measurement precision plays a role. Uncertainty is quantified numerically, providing explicit margins for error and confidence intervals. Researchers can state not only that a phenomenon is unknown but also the precise degree to which it is constrained by existing data. This precision allows questions to be refined, tested, and resolved incrementally. You may feel that understanding what is unknown is an exercise in clarity and discipline. It is not about guessing. It is about specifying boundaries, quantifying limitations, and identifying what remains measurable in the future. This process cultivates curiosity, directing attention toward tangible opportunities for discovery while avoiding conjecture. Scientists also recognize that unknowns evolve over time. As new instruments, methods, and observations emerge, previously undefined gaps may become understood phenomena. The careful cataloging of current unknowns provides a historical record of progress, marking the expansion of knowledge while maintaining awareness of remaining questions. You can sense how defining unknowns gently guides inquiry. Each question is framed with specificity, each measurement is designed to address a defined gap, and each observation is interpreted in light of established constraints. The unknown is a structured space for exploration, where curiosity is directed with clarity, rigor, and calm confidence. You begin by noticing the overall coherence of the universe. Despite subtle fluctuations, minor discrepancies in measurement, and gaps in understanding, spacetime remains remarkably stable. Planetary orbits persist, galaxies retain their structures, and cosmic expansion proceeds predictably. Observations across decades and across instruments consistently reinforce the reliability of spacetime behavior at both small and large scales. Every measurement you have encountered points toward continuity. Light from distant stars travels through space following predictable paths. Gravitational lensing bends it in ways entirely consistent with general relativity. The timing of pulsars remains precise, and spacecraft navigation relies on the stability of both space and time. These repeated confirmations provide tangible reassurance that spacetime, as we can measure it, does not fracture or behave unpredictably. Even under extreme conditions, spacetime demonstrates resilience. Near massive black holes, light bends sharply, time slows relative to distant observers, and tidal forces intensify, yet the underlying equations remain valid. Observations of black hole mergers confirm that spacetime reacts exactly as predicted, producing gravitational waves that propagate across millions of light-years. These signals match calculations to extraordinary precision, showing the consistency of the fabric of the universe. You may notice that spacetime's apparent rigidity coexists with subtle dynamism. Cosmic expansion stretches the distances between galaxies, gravitational waves ripple through the cosmos, and local spacetime curvature varies with mass. Yet these changes follow predictable mathematical laws. Nothing in the evidence indicates instability. Rather, variation occurs within a framework that is orderly, testable, and fully consistent with observations. The consistency of natural laws is another reassuring aspect. Constants such as the speed of light, Planck's constant, and Newton's gravitational constant remain stable across experiments, locations, and times. High-precision measurements confirm that these values do not fluctuate significantly. Their stability is essential for interpreting observations, building models, and predicting phenomena. Spacetime stability underpins this consistency. You notice how cumulative knowledge reinforces trust. Decades of astrophysical measurements, laboratory experiments, and satellite observations converge on a coherent picture. Minor discrepancies, such as those in expansion rate estimates or gravitational lensing studies, are within well-understood statistical uncertainties. These small variations are signals for refinement, not indicators of structural failure. Even at the quantum level, where fluctuations occur naturally, spacetime remains robust. Vacuum energy, quantum uncertainty, and particle interactions do not disrupt the macroscopic consistency of the universe. The fabric of spacetime accommodates these microscale variations while maintaining predictability at observable scales. Experiments in particle physics, quantum optics, and cosmology confirm that stability persists from the very small to the very large. You can appreciate how rigorous methodology supports this understanding. Each observation is cross-checked, each anomaly scrutinized, and each model validated against multiple datasets. The iterative nature of science ensures that claims are grounded in reproducible evidence. Stability is not assumed. It is measured, tested, and confirmed repeatedly. The resilience of spacetime also emerges from long-term observations. Planetary motions are tracked over centuries, pulsar timings over decades, and cosmic microwave background measurements over decades of satellite data. The universe behaves consistently across these timescales, indicating that its structure is not only predictable but enduring. Stability persists not only spatially but temporally. You may notice that extraordinary events, such as supernovae, neutron star collisions, or black hole mergers, highlight spacetime's responsiveness rather than its fragility. The distortions and ripples produced by these events are transient, measurable, and fully in line with theoretical predictions. Spacetime absorbs energy, transmits waves, and returns to equilibrium without tearing or breaking. Observational evidence confirms the robustness of the cosmic fabric. Mathematical frameworks continue to support this conclusion. General relativity, quantum field theory, and cosmology converge in their description of spacetime under normal and extreme conditions. Deviations from predicted behavior are minor and statistically understood. No verified observation indicates any failure of the underlying principles. Models and measurements together provide reassurance of a universe that holds together. Even so, scientists remain curious. Theoretical frontiers such as quantum gravity, the interiors of black holes, and the earliest moments of the universe are still explored cautiously. Unknowns are clearly defined, measurements continue to improve, and models are refined. Curiosity does not compromise stability. It deepens understanding while respecting the reliability of what has been verified. You notice that observation and theory are inseparable in sustaining confidence. Measurements validate models, models predict measurements, and the interplay reinforces consistency. Each layer of verification, from instruments to statistical analysis, from replication to cross-disciplinary confirmation, creates a network of assurance. Stability is supported both practically and theoretically. You may feel the rhythm of scientific patience. Knowledge accumulates incrementally, understanding is refined over time, and confidence grows slowly through verification. The universe does not demand rapid judgment. It reveals itself methodically, allowing each discovery to be tested, confirmed, and integrated. The process of observation, modeling, peer review, and cautious interpretation ensures reliability at every step. Even in the face of minor discrepancies, the overall picture remains clear. Differences in measurements of cosmic expansion, gravitational wave amplitudes, or particle properties are handled through error analysis, replication, and recalibration. No discrepancy to date has indicated that spacetime itself is unstable. Instead, these small variations guide precision improvements, reinforcing confidence in the universe's integrity. You may notice that stability is not passive. Spacetime actively responds to mass, energy, and motion, creating curvature, waves, and local variations. These responses follow precise mathematical relationships that have been tested across countless observations. The universe's structure is dynamic yet coherent, flexible in interaction but steadfast in its overall behavior. You can appreciate that scientific caution ensures safety in interpretation. Even the most extraordinary or subtle phenomena are approached methodically. Measurements are verified, anomalies are tested, and conclusions are tempered by statistical confidence and independent replication. This discipline guarantees that what is understood is reliably accurate. You notice how all these factors, observational confirmation, theoretical consistency, and methodological rigor, combine to create a profound sense of order. The universe is not chaotic, unpredictable, or prone to sudden breakdown. It behaves consistently, reliably, and according to rules that are measurable, testable, and mathematically sound. Even as you reflect on the edges of knowledge, dark matter, dark energy, quantum gravity, there is comfort in knowing that the foundations of spacetime are firmly established. Unknowns do not indicate instability. They indicate opportunity for careful exploration. Stability and curiosity coexist, allowing understanding to deepen without fear of disruption. You may feel that the universe is not only comprehensible but predictably consistent. Every observation, every model, every repeated measurement reinforces this confidence. The rhythm of planetary motion, the propagation of light, the curvature of spacetime, all adhere to well-tested laws. This coherence provides a stable framework for continued inquiry. You notice that scientific discovery is ongoing, yet fundamentally safe. The structure of spacetime does not collapse under observation. It does not fracture with measurement. The universe reveals its behavior gradually, reliably, and within predictable bounds. Each new insight is integrated into a robust and stable framework, strengthening confidence while extending understanding.